All right, so section 2.2, we're going to get into basic differentiation rules. So up until now, which was just 2.1, we learned that if we've got a function, then we can find its derivative, f prime of x, which remember is the slope of a tangent line, or it's that instantaneous rate of change at any given point on that curve. We can use this limit process. So this is an important process, this limit one, to understand and be able to do, which is why we spent, almost 2 weeks on the first section of this chapter. But now I'm going to show you some really awesome shortcuts that will take this whole long, complicated limit process and simplify it to a matter of seconds to find the derivative, as opposed to several minutes potentially going through this limit process. So you will definitely enjoy these shortcuts. So let's talk about the constant rule first. So the derivative of a constant is 0. I'm going to say that again, but instead of saying derivative, I'm going to say slope of a tangent line. The slope of a tangent line of a constant is 0. So let's think about what a function that is just a constant looks like. A function that's just a constant, let's say y equals 3. Think about what that looks like. It's a vertical or a horizontal line, and y equals 3 all the time. So this is a horizontal line. Think about the slope of that function at any given point. This has a slope of 0 always, no matter what. So that's why we have something called the constant rule, which just specifies the derivative of any constant, which remember, the function would just be a horizontal line at whatever that constant is 0. So that's why any constant has a derivative of 0, because its slope is already 0 the entire time. So in example 1 here, we have f of x equals 5. That's a horizontal line at 5. So we know f prime of x, the slope of that function, regardless of what x is always 0. Same with number 2, we have f of x equals 3 pi squared. This is still just a number. This is still a constant. Pi is a real number, which means the derivative of that function, because that's just a horizontal line, is 0. So it's a very simple one to start out with. Now we're going to get into the power rule, which is this wonderful shortcut, and this is the one I know you'll enjoy. So the power rule. Lots of notation here, but I will simplify it. We are not going to go through the proof. The proof is provided for you here if you're interested. I'm going to try and keep this as simple as possible. So I'm going to show you the power rule and then we'll practice it. The power rule. So remember, this d over dx is another way of writing notation for a derivative of a function. The power rule says that the derivative of x raised to the nth power, so x is our variable, n is whatever power it is. The derivative of that is simply, we take this exponent, it becomes the coefficient of x, and the new exponent is 1 less than whatever it was before. So we see the original is x to the n, the derivative of x to the n comes down front, it's now the coefficient of x, and the new power of x is just 1 less than whatever it began with. And then this right here is just written in the same way, or the same thing, just written f prime of x to the n. So let's look at some examples. Let's jump right into this example down here. So number 1, we see f of x equals x cubed. That means the derivative of x, f prime of x, according to this power rule we just saw, is that I take my exponent 3, that was the n up here, it becomes my new coefficient of x, so that the derivative would be 3 times x squared, because the new power is 1 less than whatever it was before. It was 3, so now it's 2. How awesome is it that we just found the derivative in a couple of seconds rather than going through that entire limit process, which we could, but these shortcuts make it much faster and much easier. So let's look at number 2. We've got f of x equals x to the 6th. That means f prime of x equals, so remember the exponent comes down, the 6 comes down, it's the new coefficient, and the power is 1 less than the original. So f prime of x is 6x to the 5th. So before I move on, let's just recap the concept that's happening right here. So with number 2, x to the 6th. So this is a funky graph that looks kind of like a a parabola, but it flattens out a lot. So let me try my best to give you a quick sketch of this. This graph goes through 0, 0, and then it goes through 1, 1, but it's very flat until then. Okay, so this is a very rough sketch of x to the 6th. So what we just found, the derivative, which again, remember, slope of the tangent line. Slope of tangent, which will tell us the slope at any point on this curve, x to the 6th. So if I want to know the slope or rate of change, how is x to the 6th changing at this exact point right here? All I would have to do is get that x value. Let's say it was 1.2. And if I want to know what is the rate of change right there, it's obviously growing very quickly. It's a very steep curve at that point. All I would have to do is plug 1.2 into f prime of x. So let's actually go ahead and do that. So when I evaluate f prime of 1.2, this is telling me the slope of the curve of x to the 6th at 1.2. So I would just take 1.2, raise it to the 5th power, then multiply it by 6, and I get 14.9. So let's say it's about 15. This means my slope right here is 15 to 1, meaning change in y would be 15 where change in x would be 1. So that's a very steep slope. Imagine a line with a slope of 15. It would be very steep. So we can calculate that slope simply by plugging in whatever x value we want to know about the rate of change at. So just want to remind you guys of the big picture of what we're doing here. These f prime of x derivative, that's always talking about that rate of change at an exact spot on a curve. All right, let's keep moving. So if we look at number 3 compared to 1 and 2, 1 and 2 are very simple to apply that power rule to. We just simply took the power down, subtracted 1. Bring the 6 down, subtract 1. Now let's look at what we've got. So this is not simply x raised to a power. We're looking at cubed root of x. But we have a way of writing roots as powers. So that's always going to be the first step in finding the derivative of a function that is a root. So x, the cubed root of x, is the same as writing x to the 1/3. So now we've got something that we can directly apply the power rule to. So this would mean f prime of x equals, so apply the power rule, the power comes down in front, 1/3 x, and then we subtract 1 from the old power. So this new power is going to be 1/3 minus 1. So I'm going to write that down because that's the power rule, but we have to be pretty comfortable with subtracting 1 from a fraction. And my suggestion is rewrite 1 as 3/3. So we really have 1/3 minus 3/3. This will give us a derivative of 1/3 x to the negative 2/3. So we took 1/3 and subtracted 1 to get negative 2/3. And then let's think about how we can simplify even more. So you guys studied negative exponents quite a bit. You were introduced in Math 1, and from there you built upon it. I'm going to add on just a tiny little example down here. You guys learned that when you have a negative exponent, for example, x to the negative 2, that does not result in a negative number. What that results in is a fraction. This is the same as 1/x². So that is what we need to keep in mind when we end up with answers like this, because our final answer shouldn't have any negative exponents in it. So this means what we've got is a derivative of 1/3, and then think about what I'm going to do with this x to the negative 2/3, keeping in mind what I did with x to the negative 2 here. So this is going to result in, instead of x to the negative 2/3, it would be 1/x to the positive 2/3. And then our final step could be simply rewriting it so it's a little more cohesive. So this would be a single fraction, 1 divided by 3x to the 2/3. This is fine. It's totally fine if your answer has exponents that are fractions. We just don't want exponents that are negative. So anytime you get a negative exponent, you need to rewrite that as a fraction to simplify your answer. Some of you may realize or remember that x to the 2/3, let me draw another little x to the 2/3. Remember, we could think of that as two different exponents. We could think of that as x squared raised to the 1/3. If I break apart this 2/3, remember an exponent raised to an exponent, you're just multiplying those. So this would be, I would multiply 2 times 1/3, which is 2/3. So there have been times where you're simplifying things like this, and we know that x squared, this 1/3, remember that's cube root. So we could write this finally as the cubed root of x squared. That would be totally fine if you wrote that in the denominator instead of x to the 2/3, but you are totally fine to leave it like a fractional exponent. But if you choose to write it as roots, that's fine too, but this is enough. Okay, let's look at another one, number 4. We've got 1 over x squared. So when it comes to applying the simple basic power rule, we need to rewrite this as x to a power. So just like, I mean, this one's kind of done for you because I accidentally did the exact same fraction right there. But f of x, 1 over x squared, we can write that instead of 1 over x squared, can write it as 1 over x to the negative 2. So you need to be really comfortable going back and forth with exponents as positive exponents in the denominator of a fraction and changing that to a negative exponent. So rewrite it and then complete the derivative using the power rule. So this would be, we take the power of negative 2 down front, and then we subtract 1. It was negative 2, we subtract 1 from that, and now it's negative 3. So our derivative is negative 2x to the negative 3, but we shouldn't have any negative exponents in our final answer. So remember, we're going to rewrite it as a fraction. So that would mean the derivative is negative 2, and then instead of x to the negative 3, it would be times 1 over x to the positive 3. And then rewriting that one final time just as one fraction. The derivative is f prime of x equals negative 2 over x cubed. So that's it. So when you have, the power rule is awesome. It just saves you a ton of time. But what we need to keep in mind is it's not always going to be a nice clean example like numbers 1 and 2 where it's simply x raised to a power. If you have roots or fractions, the first thing you need to do is rewrite it as x to a power. So if you've got any spots, any room on your page, I would like you guys to write down with roots and fractions, how do we handle that? So just to summarize, when you take the derivative of roots or fractions with x in the denominator, we will follow these steps. Rewrite it using powers, x to a power. So in order to use the power rule, you have to write it as x raised to some power. Then you can apply the power rule. So once you do that, you differentiate using power rule. Then when you're done, remember we need to rewrite it back to fractions and roots like we did here. We applied the power rule here, and then we had to rewrite it as the fraction instead of x to the negative 3rd. So rewrite back to fractions and roots. Fractions or roots. Okay. All right, let's do some more practice with the power rule. So flip on over to the next page. All right, so the constant multiple rule, we're going to combine this with the power rule. The constant multiple rule, so that just means we're going to apply the power rule, but what if we have a constant out front, this c, or an example one, this 3 out front right here. This tells us that in order to take the derivative of that, let's move over here so we're looking at the f prime. F prime of a constant times a function of x, I'm just going to multiply that constant by whatever the derivative is. So what that means is with this first example, 3x to the 4th, I'm just going to apply the power rule. So f prime of x, when I apply the power rule, remember that 4 comes down in front. It's the new coefficient of x, and the 3 is out there it's going to be multiplied by whatever the derivative is. So the 3 gets multiplied by the 4, and then you subtract 1 from 4 to get the new exponent of 3. So this derivative simplifies to 12x cubed. So the constant multiple rule just says if there's a constant out front of your function, you just multiply it by the derivative of whatever the function on x is. So let's look at another couple of examples to solidify our understanding of this. Number 2, we've got negative 2x cubed. The derivative of that, remember we take the 3 down and we're actually going to multiply it by the negative 2. So it's actually negative 2 times 3x squared. So that simplifies to negative 6x squared. Number 3, f of x equals x cubed over 5. Now this one looks a little different. What is the coefficient of x cubed? Because x cubed we can easily find the derivative of. But let's think about when you divide that by 5, let's just rewrite that as 1/5 times x cubed. Now it makes a little more sense to apply this constant multiple rule. So when I take the derivative of this, remember this 3 comes down and I'm going to multiply that by the 1/5. So the derivative f prime of x equals 3/5, so 3 times 1/5 times x squared. And we can simplify this just by writing it as 3x squared over 5. So all I did there was just think of x squared as x squared over 1, and then I multiply the numerators, 3 times x squared and 5 times 1. All right, let's combine this idea in number 4. So now we're looking at 1 over 3 times the square root of x. So if possible, again, just like in that last set of problems on the bottom of the first page, we need to rewrite this so that we can use the power rule. So if we're thinking about a coefficient of our function, we can pull that 1/3 out, and then we've got 1 over the square root of x. So the first thing I'm going to do is rewrite the square root of x as x to a power. So just to reiterate, in order to apply the power rule, I need to write our function as a power of x. So that would be x to the 1/2. But I still am not ready to apply the power rule because this is a fraction and I just want this simply to be x to a power. So to rewrite this again, f of x, I haven't even found the derivative yet, I'm just rewriting our function first. That's going to be 1/3 times x to the negative 1/2. Now I'm ready to find the derivative of f of x. So now we can apply the power rule combined with this constant multiple rule. So f prime of x, I'm taking my negative 1/2, the power, bringing it down, and it's going to be multiplied by 1/3. So that would give me a product of negative 1 over 6 when I multiply negative 1/2 times 1/3 times x raised to the power of negative 1/2 minus 1. So negative 1/2 minus 1, so I'm just going to write 1 as 2 over 2. This would give me a derivative of negative 1/6 x to the negative 3/2. So I've got two things going on here. I've got my coefficient, it's negative 1/6, but I've got this negative exponent, and we don't want negative exponents. So to rewrite my final answer here, I need to fix that. So my final derivative would be, I need to rewrite this x to the negative 3/2 as a fraction, which would be 1 over x to the positive 3/2. So that means my final derivative would be negative 1 divided by 6x to the positive 3/2. Okay, so hopefully you guys are seeing how I got that. So this negative 1/6 is right here, and then x to the negative 3/2 becomes 1 over x to the positive 3/2, and then you can just multiply those two denominators to get this single fraction. All right, let's look at number 5. We've got 3 times the cubed root of x. Again, step 1 is always rewrite these functions as x to some power. So that would actually be rewritten as 3 times x to the power, instead of the cubed root, we can write to the power of 1/3. Now we can take the derivative of this. And let me separate that off here. So the derivative would be f prime of x equals, we take our power, we bring it down front using the power rule and multiply 1/3 times 3. Well, that's just 1. So that would just be x raised to the power of 1/3 minus 1, so 1/3 minus 3/3, and that gives us a resulting derivative of x to the negative 2/3, but remember, we cannot write our final answers with negative exponents, so just one final simplification here will give us our derivative of 1 over x to the positive 2/3. All right, I do want to get through number 6 as well before we move on. So again, a lot of this is just rewriting in a clever way so that you can apply the power rule. So right with number 6, we're looking at f of x equals negative 6 over 3x to the 4th. Let's rewrite that and think of that as negative 6 over 3. So I'm kind of isolating that negative 6 over 3 times 1 over x to the 4th. And then what I can do is simplify this in a way that makes the power rule very easy to apply. So negative 6/3 is just negative 2. And then 1 over x to the 4th would be x to the negative 4. So all I've done is just rewrite this whole thing. So the negative 6/3 simplifies to negative 2. And x to the 4th in the denominator I can rewrite as times x to the negative 4. Now the power rule is very easy to apply. And we can get the derivative f prime of x equals, take the negative 4, multiply by negative 2, and you get positive 8 x to the negative 5th. So you're subtracting 1 from negative 4. The last step then would be rewrite this x to the negative 5 as 1 over x to the 5th. So this gives you a final derivative of 8 over x to the positive 5th. Okay, next is the sum and difference rule, and it's not going to overcomplicate things. All it's saying is that when you've got a function with several different terms, so instead of just a single operation on x, you've got a couple of them added or subtracted together, all you have to do is take the derivative of each individual piece and then add or subtract them, just like the function is doing. So in example 1, f of x equals x to the 4th plus 12x. All we have to do to find the derivative of that is handle each thing separated by the plus separately and find the derivative of each piece. So the derivative of this would be f prime of x equals the derivative of x to the 4th, which is 4x cubed, plus the derivative of 12x. Let's think about that because we haven't handled something where it's just, if I have 12x and I'm looking for the derivative of that, remember I take the current exponent, which is 1, bring it down to multiply by the 12, so which would be 12 times 1, x to the 1 minus 1, which is 0. So the derivative of 12x is 12x to the 0, but x to the 0 is just 1, so the derivative of 12x is just 12. So in fact, that's how it's going to be with any constant or coefficient of x. If the exponent of x is 1, then the derivative is just that coefficient itself. So that's it. We've taken the derivative of each of the two pieces of that function, and we're done. Let's look at number 2. So we've got f of x, and then we've got several pieces. We've got x cubed, 3x squared, negative 5x, and 1. So what I just showed you here with this 12x and how its derivative is 12, think about 12x. What is that? If I isolated that as a function, y equals 12x, that's a line with a slope of 12, meaning its derivative or slope is always 12. Okay, now we'll move on to number 2. So the derivative of this, we just apply the power rule to each and every piece of it. So x cubed has a derivative of 3x squared. Ironically, the next term is 3x squared, and the derivative of that, I would bring the 2 down, multiply by the 3, so that would be 6x to the first, because I'm taking this 2 and subtracting 1. So let me just color code things. This x cubed has a derivative of 3x squared. 3x squared has a derivative of 6x. Negative 5x has a derivative of negative 5, because negative 5x is linear. Its slope is always negative 5. And then remember what the slope of a constant is. This is the constant 1 has a slope of 0. So I would add a plus 0, but we don't have to actually write the plus 0. So this is our final derivative. We've taken the derivative of each piece of the function. So jumping to number 3, I've got the function negative, I forgot all about my lightsabers because they're distracting, but they're fun. Okay, so negative 1/3, notice there's no x term right here, so that is technically a constant. So the derivative of negative 1/3 is just 0, minus 3 over x squared. So we need to rewrite this, because again, we always want to rewrite, if we can, as x to a power. So we've got negative 1/3 minus 3x to the negative 2. So I've rewritten 3 over x squared as 3 times x to the negative 2. Now I can apply the power rule and differentiate. So the derivative would be the derivative of negative 1/3, which is 0 because there's no x term there. And then the derivative of this, so I'm taking my negative 2, bring it down, it multiplies by negative 3. That would result in a positive 6x to the negative 3rd power because I'm subtracting 1 from negative 2. So that's how we differentiate, but I just need to rewrite because I still have this negative exponent here. So the derivative would be f prime of x equals, so 6 is not part of this function here. 6 is in the numerator of my final answer. 6 over 1 times x to the 1 over x to the positive 3rd. So we can write that as a single fraction, 6 over x cubed. Okay, so number 4, we've got the function is the quantity 3x minus 2 squared. So again, in order to apply the power rule, the function needs to be written as simply x to a power, but this is 3x minus 2 and then raised to a power, so we cannot apply the power rule yet, but we know how to rewrite 3x minus 2 squared, because all that's doing is taking 3x minus 2 and multiplying it by itself. So it's 3x minus 2 times 3x minus 2. So this we can rewrite and then apply the power rule. So this we would rewrite by, you could use an area model, or if you're comfortable with just doing the distribution, 3x squared times 3x, or 3x times 3x, that would be 9x squared. 3x times negative 2 is negative 6x. Negative 2 times 3x, that's another negative 6x. And then negative 2 times negative 2 would be plus 4. So this gives us a final function that we can apply the power rule to. So we've got 9x squared minus 12x plus 4. Then we can directly apply that power rule. So once we rewrite it, so again, we've got something that's a quantity squared, rewrite it, then apply the power rule. So that would give us the derivative of applying the power rule to bring that down, multiply by 9, it would be 18x to the first, minus the derivative of 12x, which is just negative 12, plus the derivative of 4, which is just 0. So this is the derivative, 18x minus 12. So sometimes you will need to do a little bit of legwork of rewriting that original function as individual powers of x, then apply the power rule. So that's a good glimpse at the power rule, and it makes finding derivatives way, way, way faster than that limit process. This is where I'm going to stop for part 1 of the 2.2 notes. It's a very long section, so I might even have to split this into 3 parts because I'm trying to keep these notes closer to 30 minutes per video. So I'm going to stop here. If you want to get started on the 2.2 worksheet, you definitely can. You won't be able to do the ones with trig functions yet, but if you do get started on the homework, which I would suggest trying some, you could try numbers 1 through 8. You can also do numbers 12, 13, 14, 15, 16, yeah. You can do all of these. So I would really encourage you to work through these before watching part 2 of the notes, just because this will get you, first of all, you'll finish half of the homework and solidify your understanding of the power rule before moving on to the rest of 2.2.